So for today, that's what we're going to use. To log into Sandbox, basically just use SSH, and we'll enable your X forwarding and put your username and add sandbox.nas.nas.gov. By the way, NAS stands for NASA Advanced Supercomputing System, something like that. Yeah. I log on to my accounts, so once you to your home directory, you can, I already said the link, you can cd into summer school 2016, and you can source the environment that help you to set up the Python and some other stuff, and you can also use this module command and to take a look. And we already have open NPI there, so you can load the module as well. Later on, we're talking about how to use NPI to do a model test or parallel programming. Okay, all right. Now, this is basically under the summer school 2016. We have different directories. Today, we're going to talk about point-based BIOS correction. So just change directly to this here. We have two cases. One is for Moffett field, which is here at NASA Ames. Another one is from a place from India. So I'm going to use this India case as the example here. So, but I leave the Moffett field as an exercise afterwards for my lecture. Okay. All right. So if you cd into this space or this folder, you see we have three directories. One is EC, stands for BIOS correction, model, observations. So you can take a look at the observation data. So which is just basically text file, tabular, from 1981 all the way to 2015. I think the data is from some weather stations, even already pre-processed. This is the data, how they look like. So we have, I just picked the Tmax, Tmin, and precipitation. So these are daily data. The good thing you look at the data is like you notice there's basically no gaps. So this is actually special because many stations you will have gaps between them. So that's why you need to think about how to process these data. But this station is good. All right, this is observations. Now, this is the model data from CCSM4. So, it looked different because now the model from 1950s all the way to 2100, so it's longer, so it's harder. But the first thing you want to compare to see how the model actually compares to observations and see how they are different. So this is what I did. So basically, I generate the long-term climatology. So average every day, I just average all the data for first day, second day, or the June day. So now you get this climatology, daily climatology. And this is for temperature, the maximum temperature. This is for precipitation. And the green line shows the GCMs, and the red line shows the observations. This is from India, so you see very clearly we have the monsoon influence during the summer. Right? Before monsoon is hot, and during summer it's not that hot. After monsoon season, warm again. Anyway, this is very typical Indian climate, right? But right away you notice RTSM and observations, they don't actually match with each other right away, right? So the GCM looks like actually similar to larger variable seasonal cycle, right? It's hotter and colder during the beginning of the season and then get hotter. Right? And also you see actually generate a lot more precipitation than what we observed. So that's why GCM, this is actually very, very common. Models don't match with observations. So that's why we're trying to think about the way how do we actually can basically remove that bias, so people can. It will be easier for people to use those data, because these are data only we can predict or project into the future. Right? So how are we going to do that? Well, the basic idea is I'm take the Tmax as example. So I'm going to pick a day. Let's say for this day is about the June date 45, which is mid in February, right? Now I'm going to pick a day. So I want to look at historically what the climate or temperature for that day looks like, comparing them from observations with the models, right? But the question is, how many sample points do you think you can have for the historical observation period? Not many, right? So for this case, we have observations from 1981 to 2015. 35 years. So basically, you have 35 years for that. 35 points for that particular day. That's not a whole lot to generate a nice PDF, right? So that's why people will think, in order to generate them, get more sample points, we actually use a window, not just pick one day, right? So you basically design a window and say, for here, I just use maybe around 30 days, 1 month. I think, well, the whole month around mid-February probably could be representative of mid-February climate. So, and then you have a lot more data, right? 30 times 35, something give you around 1,000, right? So to increase the number of samples, then you can generate PDF, right? So this, here I just basically once I have that chunk of data, I just take a first look at the data and see how they compare it. From here you see observations. The content in all the plots of the points are actually located in the lower half, and that means the simulation is lower than the observations. Basically, let's definitely stay away from the one-to-one relationship. And then based on that, you generate PDFs. So we have model PDF, we have observation PDF. Very clear, the model data set is lower temperature than observations. There's some other interesting point. I don't know why this the lowest temperature just stopped at around 23 Celsius degree or 23 degrees Celsius. I don't know why. But anyway, so this is called PDF, the probability density function. And then we can also generate a cumulative probability, right? So basically this says what is the chance for mid-February temperature will lower than 23? Not many, right? Most times it's higher than 23 degrees Celsius. If you ask, well, what is the chance the temperature will be actually lower than 30 degrees? So in the model, you will see it's a lot, maybe more than 80% the chance the temperature is lower than 80 degrees. But in observations, it's only about, or even less than 40% of the chance you get temperature lower than 30 degrees. So that's the difference, shows how these things are different. Now, so we know the model underestimates our temperature as compared to the observation. So how can we actually correct the model results? That's our goal, right? We're trying to adjust the model results. So in order to do that, we use the CDF and we use something called, very popular technique called the quantum mapping. So first, let's see, from the model output, we found a day. The model says, okay, so today is 29 degrees Celsius. Okay? Now, we're going to find what is the chance in the model, in the model simulations, what is the probability the model simulated temperature were lower than 29. So basically, draw a line to the CDF and to find that point. So basically, it says almost 78% of the temperature in the model simulation were lower than 29. Now, we can take 78. So we ask the question, what is the temperature when in the observations 78% chance is lower than that temperature? You actually draw a line back to this red curve, the CDF, right? So look at that point and then draw it down and see, okay, so it's about 32.5 degrees Celsius. That's in the observations when the temperature is 32.5 and 78% of the observed temperature or lower than that. So that gives us some link. So we're talking about the climate or the weather range. We know when we're talking about 78, probability, the temperature range in observation is 32.5 and the GCM is about 29. So if we're trying to correct the GCM, we're going to assign this number back to observations. So that's called basically the quantum mapping. So that's a basic idea. It's fairly straightforward, right? Yeah. I mean, there are some advantages of this, because when you do quantum mapping, basically you don't care about the PDF or the shape of the PDF. You guys can go actually to read the papers or maybe some online resource about that. But anyway, that's why people use quantum mapping a lot. There are some other things you can do anyway. So let's take a look at the results first. So the blue dots are from before correction. We know the simulate underestimate. But after the bias correction, the same data after remapping, so you see it's largely on this 1-1 line, right? So that's just what we want to do, right? Okay. Now, after do the bias correction, you can take a look. You can regenerate the PDF and also the CDF. The CDF, of course, will be very similar. That's what we're trying to do. Basically, after we bias correct the data, and then we generate a very similar distribution, right? So remember, this is just for one day, right? We just pick one day, mid-February, and then take the window about 30 days. This is for that day.
And the model is just one particular.
Yeah, this is just a particular model.
So it's not an ensemble.
No, not
Okay.
yet. Not yet. So you want to do the whole year, and you have to repeat the whole process for 365 days, right? Now you want to do ensemble model, you have to repeat the whole process for all the models. And you want to do it for every grid point, you have to repeat the process for every grid point. And there are also, G7 5 will have different scenarios, right? Different RCP scenarios, so you have to repeat the whole thing. So you can imagine that that's why we need a supercomputer to do these things. And we generate a lot of data. But anyway, so that's, you basically can imagine, like, you just move the window and then get the whole thing down. Now, here's some, very detailed questions. Let's say you move the window to end. Where do you want to put the window? It's like, Because this upper limit could move out, right? So, but you can use here. Right? So these are very detailed stuff you can use. But anyway. Right. So that's about the basic idea. Now, the Python code, you take a look, if you're already in the sandbox, they're basic, very basic code. The first one is, I want you to just test this, the bias correction test, py.py. It's just what I use to generate those plots. Okay. So it's a Python code, as I said. The quality of the code is not professional. I won't call it professional, but it's not terribly bad. I mean, it's reasonable. Just because I use some hard codes, these parameters, but it can easily be taken care of. So now magic is here. So if you go down about 9, I define many functions, but then you go down, the main function is not that long. It's just about this 9, where that's the magic. Basically, I do bias correction by, I call it CDF match or CDF map. You can change the name. That's you input observation model data, some other accelerated information. Let's see if you want to detrain or not. That's actually a discussion question. So that's where you do the bias correction. We can take a look at that function. It's not that long, only 3 lines of code, so it's actually fairly easy. First of all, do some data cleaning process, and then the main thing is just generate CDFs for observations and for models, right? And you map the model data, the value of the GCM output to the CDF probability, and use that probability to map back to the values from the CDF observations back to the model to correct the model data, and you take care of the trend, things like that. You're done. This is just for one day. That's it. You add one more loop, and you can do the code the year. Yeah. So that's about the basic, the code description. Now you can actually link 2 exercises. First one is just use the bias correction code to process the data for multi-viewed. Now we actually provide the observations and GCMs. So it should take about 5 or 10 minutes to finish that, but it can take longer if you want to do more. But definitely you can do more. I don't know what this is about. It's supposed to be 2. Now, see, something like I provide some another code to actually analyze the changes of heat waves, how heat waves change over the 100 years. What are their frequency and intensity, how they are going to change over the rest of the century. So you can use that code to analyze some of those changes too. Right. So these are the 2 exercises. Now, as I said, the idea about bias correction is very easy, but there's something more you need to think about beyond what I just described. The first one is, these are actually important, because the first one is why we're doing quantum mapping with CDFs. We actually made the assumption that the PDF or CDF are between historical time and the future, they will change, right? If they're going to change, you cannot map it, right? Because it's already changed. But we know, hey, climate is changing, so how can you do that? How can you make that an assumption, right? So definitely there's something actually to be taken care of. So think about how should we address that issue. There's no perfect solution. It's still a research problem. We don't have the perfect way to address that issue. But just think about, from your point of view, how do you want to solve that problem? Another one is, I don't know why this thing's changed. Another one is, when we talk about observations and GCMs, we said GCMs is 100 by 100 kilometer. Basically, it represents some sort of mean status over that grid cell, right? But our observations will come from station data. One station is just that particular location. That means the observation data could have a lot more variability than GCMs. Now, should we actually directly compare them? Is that a good way to do it, or we need to do some pre-process when we compare GCM to let's see, observations? That's another issue to think about, because most of the time people are saying we need to compare apple to apple, origin to origin, right? Somehow we're here. If you directly compare station data with data from one single station to GCM, you kind of like compare your origin to apple. So you have to take care of that problem too. There are some more. Now, I mentioned right now today we're just doing hands-on on this point-based bias correction. But in application, we need to take the close resolution GCM to high resolution grid data, right? So in order to do that, you have to somehow to disaggregate data spatially, or sometimes I call it interpolate or extrapolate. Depends on different way you look at it. But how are you going to do that? It's actually, when you think about it, it's not that easy. The first thing that came to my mind when I thought, I just do a linear interpolation. But turned out not many people do that, because obviously there's some drawback of that linear interpolation. Linear or bilinear, almost no one do that now for downscaling. They're using some algorithm called, one of them is called spatial disaggregation SP. Or use constructed analogs. So this is another technique from the metrology community of literature. Now this is something new called localized constructed analogs. Again, developed by Dave Pierce from Scripps. So think about how do we actually, once we bias correct the GCM, how do we actually generate high resolution grid data from that information? It's not easy to do. And again, in this field, there's no perfect solution. Otherwise, everyone uses one algorithm. But anyway. Now, the last one is, now we have different downscaling methodology or algorithms, and people generate different data sets. All of a sudden, you found you're in a situation you have multiple data sets to choose from, right? So which one to choose? And how do you evaluate your uncertainties? Again, this is actually a very difficult research problem. And as I mentioned before, that NCPP 2013 workshop was dedicated on that particular topic. So one of the solutions is an experiment designed by Keith Dickinson from Princeton, and he called it perfect model experiment, which is actually very interesting. You can find his talk on this website, and he also just published a paper this year, so maybe you can follow on their paper to read that paper too. Very good idea and a very interesting experiment. So that's about the more idea or the question to think about as you guys start to do research by your own later on, right? So you have to think about beyond the basics. Anyway, so but that's about my lecture today. Thank you guys, and stay tuned for more our lectures to come. We're going to talk about our Google Earth Engine or the AWS, those things. Anyway, thank you very much. All right.